Okay, so everybody having a good day? Learning some things? Enjoying it? No, good. All the decks that we have here are going to be available. They're on the Redgate event page for this site, so if you go to sqlinthecity.redgate.com/Pasadena/whatever, you can get all the decks. And then we're going to have some videos as well. So Redgate has a YouTube page at Redgate Videos, all one word. And so we've got various things up there, but we'll have some of the stuff from today and other stops we do this week. So if you miss a session, you can go check there. Hopefully we'll have them all up there. All right, here we go. So we're talking encryption today. This is kind of a basic look at all different kinds of encryption in SQL Server and all your various options. Is anybody here using encryption out of curiosity? A few of you. All right, cool. So I'm Steve Jones. I run SQLServerCentral.com, and I also work for Redgate Software as an evangelist. And so those are my two jobs. Here is the agenda of what we're going to kind of cover. It's a lot to cover, so we're going to try to go a little bit quickly, but if you have questions, please feel free to ask. So, does anybody know what this is?
Enigma machine.
You guys are smart out here. The Enigma machine from World War II. The Germans built this machine, and it was actually fairly uncrackable encryption back in the 1940s. Until we actually captured one of these machines, we struggled with how this worked and how to break it. And these days, it's fairly trivial encryption for the processing power we have today. Encryption is essentially where we take data that we can read and we turn it into something that we can't read, and from which the original source can't easily be derived. That's here's kind of a formal definition, but essentially we're taking plain text, the stuff that we want to protect or prevent people from reading. We turn it into something that is hopefully fairly random, and they can't extract the plain text. Whether we can go back to the plain text or not just depends on the way we do the cryptography that's involved. So, simple cipher, a lot of you probably used a simple cipher like this in elementary school, high school, something like that. It's a substitution cipher. If you do the substitution of letters, you get something. We don't use this anymore because your phone could crack this in milliseconds, right? So we tend to use things more like this, and we'll talk about how this works a little bit later. So what can we do in SQL Server? I have a little bit of a diagram here that kind of covers from the client over to the SQL Server instance. And I want to talk about where we can encrypt and where we can't. Now, assuming that we give the client the encrypted data and the key to decrypt it, because otherwise the encrypted data is fairly useless. If we send both of those pieces of information to the client file system, we can't protect the data at all. We can't do any kind of encryption there. So you can't assume that anything you send to the client is actually going to stay secure. The same thing would go about in terms of the client here. Even if it hits their screen only, there's a possibility that they could do some encryption if the key is also sent to the client. So you can't protect those. We can, however, secure the communication. So from any third parties from listening in, we can secure data in SQL Server memory. We can keep it encrypted there. We can do the data files and the backup files as well. So primarily, we're going to be talking about these four areas and the ways in which we can do encryption. Here is a diagram from MSDN. Don't bother trying to read it, really. You can download it. I have it in the deck, so if you want to know what it is. But essentially, there's a hierarchy that starts from the Windows DP API, Data Protection API, which has proven to be fairly strong. In the last decade or so, there have been no cryptographic weaknesses there. That protects everything else. We have various keys that we use to protect our data. These boxes that are light gray or blue are password, meaning that at various points in time, I could use a password to secure the rest of my encryption. So I could use a password to secure a certificate, to secure a symmetric key, to secure data, or I could use a password just to secure my data. So, everybody with me? Good. So let's talk about communications. Communications involve encrypting the data that's sent along the network wire or the wireless traffic, however we do it today. You essentially have two options to do this with SQL Server. You can use SSL, which is the same SSL encryption used on all your web browsers, or you can use IPsec, which occurs at the Windows layer or lower down the stack. If you get the choice, please use IPsec. It's much simpler and it's easier. It covers end-to-end encryption better. If you have to move an instance or do something else, IPsec just works really well, but it is kind of bound within your infrastructure or within the devices that can support IPsec. if you have to go outside to other clients, you may have to go to SSL. I'm not going to talk about IPsec because that's really a Windows administrator issue. For SSL, essentially what we have to do is we have to get a certificate that we install on the SQL Server host on the Windows machine. This is the same type of certificate you would use for a web server. Please do not use self-signed certificates here. Please go buy a real certificate if you care about encrypting your data. The reason is those certificates can be validated by the client as authentic certificates. If you create your own certificate, the client has no way to know if somebody were to replace that certificate or to impersonate your machine because they have no hierarchy of trust. If any of you have ever gone to Amazon or some other website for SSL and you get a pop-up that says this certificate has expired or we don't know what it is, you should be very concerned about ever sticking any PII, financial, medical data in there because you don't know if the other server you're communicating with is actually the server you think it is. It's entirely possible that somebody has impersonated Amazon.com or any of these other sites and are intercepting your traffic. So that's a serious message if you're trying to be secure. Please don't put your credit cards in or anything else. That's why you wouldn't do it here for the same reason. Now the certificate that you use here has to be valid, meaning it has to be unexpired. Certificates have a begin and an end date. If this expires, you can't connect anymore with SSL. It's not a big deal. You can connect locally. You can reconfigure things if you need to. The rules in VOL for setting this up are fairly mundane. It's just a do step A, step B, step C. It's very easy to do. Oops, that's not what I want to do. So I'm not going to show you how to do that, but essentially if you just follow the steps here, it's pretty easy to do. In your configuration manager in SQL Server, you would pick the certificate you want to use, turn encryption on, and then your clients could connect that way. Any questions on SSL? No. It's pretty simple stuff. Is anybody using SSL? It's not very common. A few people are. Right. So let's move on to TDE, or Transparent Data Encryption. Microsoft introduced this in SQL Server 2008, so we've had it for 2 or 3 versions. The idea here was that we wanted to enable encryption in SQL Server without requiring any code changes whatsoever, hence the transparent name and note. All the other encryption that we do will require code changes, some kind of alteration to the way you've written your application or your database code. TDE is completely transparent. So when you implement it, what happens is it encrypts all of your data files, your log files, it encrypts your backups as well, and so it protects you from losing any of those physical files or anybody accessing. However, if you connect to SQL Server with a valid account, it looks like a normal SQL Server database. You can see all the data as long as you have rights to connect to the tables or views, execute the sort procedures. Everything else works as you would expect it to. TempDB is also encrypted. There's a little bit of overhead for TDE, which means that there's also overhead for TempDB. If you have an instance with a large number of databases and you're trying to just protect one, just be aware that TempDB will be encrypted for all operations on that instance, for all databases. And if you have a busy server, a busy workload, that could be an impact to your system, so you have to be aware of that. Anything outside of the SQL Server, outside of the instance itself, is not encrypted. Any data you replicate off is not encrypted. Any data that's stored in file stream containers is not encrypted. All right. You can do end-to-end encryption because I could TDE my source database, my publisher. I could use SSL encryption or IPsec encryption across the wire, and I could TDE separately my subscriber database, so I could have encryption, but I would have to do those 3 steps separately. All right? So, how do we do this? I'm going to show you how to do this in a minute. Essentially, we are going to create a database encryption key that's going to encrypt our database, and then we protect that with a certificate on the instance. That certificate has to be available in any kind of situation where I have to restore this database. If I don't have the certificate, I'm not restoring this database. If I don't have the certificate, it's what Grant would call an RGE. Does anybody know what an RGE is? It is a resume generating event. You will not be calling Microsoft for support because they will not help you. If you lose a certificate, you lose that data. If you don't have a backup copy you can recover with, it will be an RGE for many of you. All right, so for all this encryption stuff, if you have keys, you should be dead serious about backing them up and keep control of them because otherwise nobody's helping you get this data back. All right, we're not going to go over that. Let's look at how TDE actually works. So we don't want to look at monitoring, we want to look at TDE. So I've got an instance here on my laptop. I'm going to create a database, create a table, and stick some data in it. Nothing magic here, what I'm doing. I'm essentially just creating a table so that I have a pattern of stuff that I can find in the file. Let's make a backup of this, because backups are good, right? Everybody likes backups? No? I know, it's after lunch, I'm sorry. We're going to detach this database now. And then, I'm going to open up my hex editor. Anybody ever used a hex editor? All the old people have.
That's right.
Makes me feel old too.
Sorry.
I know, it is what it is, right? So let's, just want to make sure I'm in the right place. Let's open up my file. Here's my MDF file. And if I come over here, you can actually see in the header, this is all the hex data of the actual file that's being read. And then here's the decode into human readable ASCII text. The name of my database is actually stuck in there. That's never encrypted, that's header information. If I scroll through here a bit, you can see I have a lot of just essentially blank information, all these zeros through here. If I click the right button, if I search for my name, I find my name in the MDF file. This is a raw MDF file. You can see my name is there, and then you can see data after it. And this is the row structure actually stored on disk. Okay? If I were to come over here and pop open that backup file, I would see a very similar thing. I see Microsoft SQL Server, various information. I see my files. If I go back up, you actually see the pathing of the files. This is where the with move command comes from. There's the path where the stuff's stored. And if I look for my name again, I'll find it in there. Right? Backup's completely unprotected. Anybody can read this stuff. I have a social security number in there, anything else. If you use the with media password command in your backups, that does not stop this from happening. I can still read all this data. That password, by the way, is deprecated. It's not available. Discontinued in 2012 and beyond, so you can't even use it. But 2008, all that prevents is me from restoring it with the SQL Server code if I don't have the password. I can use a hex editor and I can read all of that data. So nothing is protected. This is why losing backup tapes or losing physical disks is a bad idea, or it's a problem, losing a laptop. All right? So, obviously we want to do something about that. So let's reattach our database. I'll have all this code for you. There's nothing magic about it, what I'm doing here. It's working. So let's start encryption setup. I've linked in the procedure here. Here's where we start. We create a master key in our master database. If you already do encryption, you may have a master key there. It doesn't hurt. If I create this, let's do this. We'll talk a little more about what a master key does, but this essentially just gives me a starting point in that database to encrypt anything further with it. If I run this again, I just get an error message. It doesn't hurt anything. All right. Next, I create a certificate. This is what would be known as a self-signed certificate. Okay? I created it. That means that you're trusting me with that this certificate actually implies that it's protecting something, that I am who I say I am. This is not the certificate that you would want to use for SSL or any off-server communications. You can use this for testing. If you're testing your dev environment, it works just fine. Just don't use it when you're really trying to protect data. Now, I use my database, so I'm going to create the database encryption key. Well, that was bad. Did I not execute this? I thought I did.
Looks like there's an underscore after TDE on the...
Should be there.
It's missing. The TDE is TDE primary, no underscore between TDE and primary.
That's right. Oh no. Oh, here. There's a better way to fix this. Let's not do that. Let's start over. And let's go back to master and do this. Okay, good. Let's go back up now. Somewhere I broke something, but it's all right. So create a master key, create a certificate. Good. Good. All right, so it worked. I must have just hit something incorrect. You'll notice that I created my database encryption key, and then I get this warning here. This certificate used for encrypting database encryption key has not been backed up. Please take that seriously. Because if you lose that certificate, if I mess up right now, I have no way to actually then decrypt the database if I turn on encryption. Okay, if something happens. So I'm going to back this up. There's a simple backup certificate command here. Now what I want to do is I'm going to do this in one batch. I'm going to show you, we're going to check the encryption status, and there's just DMVs that we queried to do this. We're going to turn encryption on, and then I'm going to run this same query again. I've got it below here, just so that I can see this happen, because it happens fairly quick on a small database. What happens here is I've created a database encryption key, so my encryption state is 1. I have not encrypted it as of yet. TempDB is set ready for encryption as well, but there's no operations occurring in TempDB. Once I turn encryption on, I get a 2. It says is encrypted, but what it really means is it's in the process of encrypting your database. The way that this works is once you turn this on, SQL Server spawns a thread and starts encrypting the data file, and it takes physical time to go through that file. While it's doing the encryption, you can still use the database and read and write from it. Everything's normal, just a little more CPU overhead. Eventually, that will be complete, and it will be set at status 3. So if I run this again now, because it will be done, it's at 3, and my database is actually encrypted. And I can prove this to you by doing the same thing we just did a minute ago. We'll go back to that same file. I can still read the name of the database. This header information is always unencrypted. It has to be there. But if I were to search for my name, I won't find it. And if I were to scroll through here, what I'm going to see is that now I don't have all zeros. I have a lot of encrypted data. If I were to make a backup and go through this again, which I can do, it's just short on time today, so I don't want to do it, but you'd see a similar thing that you wouldn't be able to read any of the data in there. Okay? Let's reattach this and perform a backup. Now, my backup file, unencrypted, encrypted. This is the one that I just did. You notice timestamp just a few minutes later. I'm going to actually copy this over to another instance. So I have another instance of SQL Server running on this machine. So if I come over here to this instance, copy this file, I have it available. Here's my second instance down here. I have no databases available. It's just a blank instance. Let's do a restore. So we'll pick that backup file. And eventually this will come up. There we go. Here's our backup file. At this point in time, you'll notice I can read the database name. I see that I can read the LSANs, the state of this backup file. But up here at the top, you'll notice I actually have an error that occurred. And if I were to go over here to this second page, I can't actually do a with move or do anything else. This error message, let me zoom in a little bit, essentially says we cannot find a certificate with a thumbprint. Thumbprint is essentially a hash that tells me which certificate it is, which means that I can't do this restore. I have no way to do this restore. Excuse me. If I were to try to do this with just a script, I would end up with just get an error because I can't read this. This is the certificate that I backed up that I must have a copy of, or I will never get anything out of this backup ever again. All right, this encryption is very strong. So what can I do? Well, let's restore this certificate over here. All right, I'm connected to my new instance. You see down here. So I need a master key again in my master database, so we'll create that. My create certificate is how I restore things. There is no restore certificate, you just create it from a file. This certificate is actually 2 different files, and I will show you where they are right now. I ran the backup before, right at the beginning I ran the backup of the certificate. There actually, a certificate is in the data file directory, not the backup directory. It's because it is, it's a secure file. They don't want any issues with this. So let's copy these, and we'll stick them over here on our other instance. I actually am going to put them in the backup directory because that's where I wrote the script. You'll notice when I do the paste that I actually have to bypass UAC permissions because these files are not accessible by anybody with the service count for SQL Server. They're ACL to that service count. So even as an administrator, I have to take ownership of these and say, I want to actually do this operation. So we'll copy these, and then I can run my create. It works, I have a certificate. I could do the restore, any number of ways here, but I'm going to do this again just so that we can see that it actually reacts differently. And find our file. There it is. No errors, everything's there. If I come over to my other page, I can do the relocation. I can run the restore. This will complete, and then I can actually access my data. There we go. And if I use my database and run this, I have data. Is anybody impressed by that at all? You guys were looking a little asleep, that's easy stuff. We can all do that. Any questions on what that is? Yes?
Why is the key length for, if you do an encryption of AES 128, why is TempDB 256 when you look at it?
When I did, because I think for me, where's my other script? I just created that with 128, I think just for the purposes of the demo actually going quickly. Let me go up here.
No, I've done it before as well. I'm just curious.
Is it always that way?
It seems to be if you use 128, TempDB would be 256.
So my guess would be that, so we're not creating this ourselves. This is internally done for TempDB. My guess is the default is just 256. I wouldn't be surprised in 2014 if it's actually 512. I haven't tried it, but I'm guessing that is. He's saying, here's the bit length here. I chose AES 128. I could do AES 256 or AES 512 if I so chose. But I don't know. I never looked at that. I wonder if you did 512, TempDB would be 512. It'd be interesting, huh? I'll have to test that. That's a good question. Yes, sir.
So this protects your backup from unscrupulous spies, but if you have contractually, you can't let your DBA see the contents of the table, like you were browsing data there. If that's not allowed, I guess you have to do the encryption a different way, right?
So he's saying that this protects my backup files. It also protects my MDF and LDF files, but does not protect the data from the DBA or any legitimate user that can access stuff. We will talk about other ways you can potentially protect the DBA from accessing stuff. So if you just hang on a minute. Get to that. Anybody? Yes?
Just a little note, one of the most interesting feature of TDE is that it's available only on enterprise SQL Server.
That's a great question. You know that? Because it is enterprise only. It's not on Express Edition, it's not on BI Edition, it's not on Standard Edition, it's not on Compact Edition, it's not on Web Edition or Workgroup Edition or any other edition of SQL Server. It's an enterprise only feature. Please complain to Microsoft about that, it's not my fault. Yes, sir?
Well, the TDE works with the log shipping feature?
I'm sorry, I didn't quite hear.
The TDE works on the log shipping?
Does TDE work on log shipping? So TDE can work with log shipping or replication or anything else. In the case of log shipping, what you would have to do is move the certificate over to the other side like I did into the other instance. Once you had restored that certificate, then the log shipping process could work the same because SQL Server will have the certificate to be able to restore the log files that are sent across. Okay, so it will work with log shipping. Overhead is pretty small. I have some friends that do this for large retail organizations where they have fairly large instances of SQL Server, 20, 30, 40 cores, and they're pulling data from all kinds of remote locations and dealing with it encrypted. And they tend to see overhead of less than 5%. That is workload dependent. If you have larger blobs of data or just your workload is different, you could see higher overhead, so you have to prepare and test for that. I have value up here as a question mark because if you are HIPAA compliant, or bound by HIPAA or PCI or any other regulation, typically you do have to encrypt data, but they don't tell you how. TDE does usually satisfy auditors in terms of saying data is encrypted. However, any legitimate user, any DBA, any person that can hack through your website or application with SQL injection can read the data. So the protection that we're actually providing here is for a certain domain of problems. Somebody loses a backup tape, steals it, they copy an MDF, LDF file, I lose a laptop. You could do this in developer edition, by the way. It isn't developer edition. But if I lose a laptop with data on it, this protects against losing that data. However, if you're going to put data on your laptops that you care about, please use something like BitLocker or Semantic whole disk encryption. Just encrypt the whole disk. Don't just do SQL Server. There are some third-party tools that you could use for whole disk encryption. There are a couple for SQL Server that will just encrypt your files as well. And then there are many backup products. Redgate makes SQL backup. There are other backup products as well that will do encryption of your data. Yes?
Question here. So if you are generating your own certificate file, can you use the market purchase certificate and combine together?
If I'm generating my own certificate, can I use the certificate I buy and combine them together? No, I mean, you can't combine certificates. I could use those certificates. Certificate is a certificate. The difference between the certificate I create and the certificate that I buy is that the certificate I buy has some authority of trust, and there are systems in place to verify that. For example, all the major browsers have the ability to verify that a certificate was purchased, in fact, from Thought or from eTrust or from somebody else, and therefore it's valid.
So the question is here, like let's suppose you have one SQL instance and you have two different databases and you want the encryption key or certificate for both databases to the different certificate to use it. So one you want to use with your generated, one you want to use with the market purchase, and maybe the end audience or web server is different, two different. So in that scenario, can you use the combination, or like SQL doesn't allow more than one certificate to build inside the master?
So you have two different databases you want to encrypt, both of them with different keys. SQL Server has, you can have multiple certificates in there, it doesn't care. Whether they're your ones you make or whether they're ones you purchased, it doesn't really matter. You can use self-signed certificates for communications or anything else, but you're just, the security is much lower because you can't ever verify that it's actually, the other end is actually who they say they are. That's the problem. So yeah, you can have multiple certificates. Whether you purchase them or not is up to you. It depends on your security requirement. Okay, so you could, if you had 5 databases with TDE enabled, you wanted all with 5 different certificates, you can do that. Okay. Any other questions? I might have forgotten something. If you have more questions, please ask. All right, move on to hashing real quick. So hashing is a very valuable tool in computer science. We use hashing for all different kinds of things. Those of you that are CS majors have probably used hashing for writing sort algorithms. SQL Server uses hash joins where they're actually performing hashing internally. All different kinds. Some hashing is useful for cryptographic purposes, some is not. Hashing is essentially we're taking some value we have and we transform it with an algorithm and we come up with essentially a smaller value that we can manipulate better. We can have collisions, so I have my first value, my last value actually hashed to the same value. That could be beneficial or that could be problematic. It's depending on what you're trying to do with the hash. In sorting and hash joins, that collision is actually beneficial. Cryptography is really bad. We don't want collisions. Okay? So we tend to choose hash algorithms that don't generate collision. We have really 3 main algorithms in SQL Server for hashing purposes. We have hash bytes, which is useful for encryption and cryptography. We have checksum and binary checksum, which are not. Typically, those are used more for detecting changes. For example, if I send a row to a user or I'm doing an ETL process, I can run a checksum on that row, and if it comes back different than the original checksum, I know something changed. That's a valuable tool in all kinds of computer science, but not good in cryptography. There are better algorithms out there, or better ways to do things with the CLR. If you're SQL Server 2005 and later, you could implement your own version of hashing using the CLR. Now, please don't write your own hashing algorithm. Please use a well-known, well-tested hashing algorithm out there. But if you want to do something like SHA-2 or SHA-3, which aren't available in SQL Server 2005 or 2008, you could implement them via the CLR. You can use .NET, the cryptography namespace, and then use CLR to implement those in SQL Server. So let's look at how hashing works. And close this and this. And we want to look at hashing. All right, so let's look at basic hashing with hash bytes. Essentially, hash bytes is, let me scroll this up a little bit, passing in a string and giving it an algorithm and generating a result. As you can see, my string does not look like my result. I passed in the algorithm here. Okay, nothing big about that. Let me hash a couple of strings and a couple of algorithms here. I'm just going to pull it all together so we can see results. You'll see here that I've done 2 different strings with the same algorithm. I get 2 different results. We expect that. If I do the same string with SHA1 and SHA2, I get the same. Sorry, SHA and SHA1, I get the same result. They're the exact same algorithm. So don't think that the one somehow makes it better. It doesn't. However, SHA2 was added in SQL Server 2012, and I have 2 different bit strings here, and you can see that I get different results here. Okay, nothing magic there. One of the things that we don't want is we don't want people to be able to guess what's going on with our hashing. For example, one of the things people can do is take every word in a dictionary and run it through a hash algorithm, and they get a bunch of results. And then they have every word in the dictionary, and have every word, the hash of every word, and that's a table. We're really good at using tables. And then if I'm trying to figure out what password somebody has or what value they've stored, I can search for the hash. When I get a match, I then look at what word created that hash, and I have the results. Okay? I don't even have to get the original word correct. I just need a word that produces that hash. That's where collisions become very bad in cryptography. That kind of table is called a rainbow table. There are lots of password cracking programs that use exactly that. They have rainbow tables of different combinations of words and substitutions, and so if they can match up your values, then they can figure out what you put in there, which is bad. One of the ways around that is to use what we call a salt. In this case, you'll notice in my unsalted string, I've just passed a string into my hash bytes algorithm. In my salted string, I've actually added another scalar value to my hash. I could add, a variable value. I could add something from a different row. I could do all kinds of stuff. But the idea is to create something that isn't easily guessed. And so let me show you a little example of how that works in practice. So I'm going to create a little table here, users and passwords. I'm going to put a couple people in there. And I'm going to create a store procedure that validates a name and password. Okay? Pass in name and password, it compares to the table and says good or no good. Make sense? Kind of thing that applications do every day, web applications. We do this stuff all the time. Somebody goes to a website, they log in, they punch in their name and password. We execute code like this. Hopefully we've parameterized it correctly in .NET and not use dynamic SQL, but this works. If I try a different password, it doesn't work. All right, everybody with me? Okay, good. So here's the problem. My partner Andy copies his password hash to my row. He doesn't know my password. All he's done is copied the value over so that it matches up in the row. Now, when he logs in with his password in my account, it works. All right? We have had an attack without anybody decoding the password. This is why SQL injection is a huge problem in any application, because I don't have to necessarily know a password. If I can copy over something that's known to all the values in a row, like every administrator, everybody else, I have the ability to log into applications and cause damage. And SQL injection is a huge problem. We should take it very seriously in development. If I log in with my password, it doesn't work. This is also a problem. Most of you are probably administrators on your machine and your database, on your domain, somewhere else. If you ever go to log in and you type your password correctly and you're absolutely positive you have and you cannot log in, you could be the victim of an attack like this. Somebody could have changed your password without you knowing about it and logged in and done something. It could be your fellow administrator that's causing trouble, but in any case, all actions taken are under your account and audited under your account. If If you ever can't log in and you're sure you didn't change your password, you need to go check the last login time and make sure it's the time that you logged in last and not somebody else. All right? So, what can we do? I'm going to reset this table, and I'm going to alter my procedure slightly. You'll notice when I reset my names, instead of just passing in a password, I actually passed in a password plus the name of the user. I salted the values. I do the same thing when I check here. Did I run this? You're confusing me. All right. If we log in again, it works. Let's do the same attack. I'm going to do the attack and then try to log in again. Andy logging in with my account, his password, it fails this time. Okay? The reason is because of that salt is in the way. I don't know that I would necessarily choose something in the same row as my password because that's fairly trivial, right? Everybody can start trying combinations of things. But if you have a vertical partition, maybe you have a scalar value, there's other things you could do to perhaps protect you. The other thing you might do on application code is when you build this procedure, do with encryption. It's not really encryption, it's obfuscation, but it does prevent somebody from just reading the code off this production server and seeing what you used for the salt. All right? I think that's all I got here. Let's see. Oh no, checksum. So checksum, I don't want to spend a lot of time here. Like I said, it's more useful for actually checking to see if things change. The reason is because you get lots of collisions. There's a fairly trivial level of strings. If you start trying lots of different strings, you'll find tons of collisions in checksum or in binary checksum. They both work similar. If you're trying to do things where you do want to detect change, this can be fine. You know, for ETL process stuff, this works great. For cryptography, it doesn't work at all, so don't use it. All right. Any questions?
So
Anybody
whatever the solution you told, like, you can only do the database level encryption, but if you have to do the object level encryption, like a couple of tables only or stored procedures only.
We're going to talk about that in a minute, so just wait a minute. He's asking about just encrypting certain objects, so just hold on. I'll be right there. Okay. Any questions on hashing? It's not really encryption. Really, the stuff that we do with hashing for cryptography purposes is one-way hashing. That's what I was doing with the password. I can't turn that back into the password, but I don't care. For the purposes of authentication or for a lot of things we do, I can just store the hash and do that. Hashing is also valuable in doing things like, if you do the last 4 digits of the social security number, the credit card number, because hashing is indexable. Because it's deterministic, I get the same values, I can index it. The values that I get coming out of the other types of encryption we'll talk about are not deterministic, and so that means that I can't really index them, so performance dies there. Please use strongest algorithm available. This is what you get out of the box. You should use SHA-2 everywhere if you're going to do hashing. SHA-1 has been shown to have weaknesses and it has been successfully attacked. So if you're 2008, 2005, just go get a book, learn how to write a CLR store procedure, use the .NET cryptography classes, and you can implement your own SHA-2 algorithm. Okay. As a matter of fact, SQL Server sent me an article last week or this week on how you could do that, if you're interested. All right, all good? Okay. So let's talk about keys. The keys will lead us into the other types of encryption. We have all these keys in SQL Server, and we're going to kind of go through some of them. Here's how they relate in a hierarchy level. And again, they're protected at the top with Windows with a DP API, and then they flow down from there. The service master key is the first key that we run into. That protects the entire instance. The documentation is a little split here. It's either created when you install SQL Server or when you first use it. At the end of the day, it doesn't matter because you don't need it until you use it, so it's irrelevant. But you might see it either way in the documentation for different versions. Essentially, this is the key that the service account uses to then open up and start decrypting everything else inside SQL Server. You do want a backup of this key if you're trying to restore the entire instance in a DR situation, but it's not completely necessary if the other keys you have are protected by passwords. This doesn't necessarily mean you lose your job if you lose this key. Right? Not to say that you shouldn't back it up. I'm just saying, be careful. It's not critical. There's just standard DDL there that we have to do this. We can regenerate this if we need it. Regeneration of any key results in decrypting all keys that it protects and then re-encrypting them with a new key that's created, which can be time intensive. You can force this. If it can't decrypt a key, you may or may not care about that. And this is one of the places where you can protect data from a DBA. That if I have a particular database that's protected by a master key, but it's not linked to the service master key, then if I regenerate the service master key for some reason, because I'm doing key rotation or I'm moving it to a new instance, I may not want that master key linked in that specific database. I can still force this regeneration of this key, and it'll warn me. It'll say this might cause data loss. I can't, decrypt this key. It's up to you to choose whether or not you allow that or don't allow that. But there are valid reasons why you may or may not care if this you get the messages that will cause data loss. However, if you don't have other ways into any other keys and it does give you the message that it can't decrypt something, you should stop. Because if you force it to go through, then it could be serious data loss. There's not a lot more to say about that. There's standard DDL to back that up. The database master key is database specific. This is linked to a particular database. And you saw me create one on one instance for TDE, and on a different instance I created another one again in master. These are what kind of protect an individual database. This key, once you've created it, the SQL Server instance has to be able to open it in order to access the database. Typically, when we create these master keys, they're protected by the SMK, by the service master key. When you saw me create that one before, I just had create master key with a password, and that was it. That password is what allows me to open it as well. So I can drop my encryption by the service master key, which means that I have delinked these keys. So I have an instance key that opens up my instance, and then I have a database key that opens up my database. If I delink those two, SQL Server cannot open my database when it starts up. I'll get errors in the error log, can't run recovery, but DBA or anybody can't access that database. The instance can't access the database unless it has the password. This is one of the few places you can protect data from a DBA by delinking this and having the password put in by a user or by an application. In this way, the data is all protected from DBA. Now, anybody that has a password can read all the data in the database, right? As soon as they access it, the server will go through recovery, and they can get in for that session. But every other session would need to open this up. Okay? There's standard kind of commands here. You can, to open and close things, how you access the database. If you want to do it, you open up the key and open up the database. Okay? If you are moving the database as a database master key, you do need the password to restore it, or it needs to be linked to a service master key on that instance so that it can connect to it. There's not much more to say, it just has to be there. You have to have that, okay? These keys you do want to protect and back up. Any questions? I know I'm going a little fast, trying not to run out of time here. All right, symmetric keys. Here's where we really start to protect data. This is my front door at the ranch where I live in. The key that I stick in there to lock it is the key that I stick in there to unlock it. Right? This is essentially the same thing done in hardware. Code that you stuck in there, you put in there to unlock it, is reset with hardware back to the exact same code when you lock it. Okay? Symmetric encryption. These keys are created in a database, and I know I told you that you always have to back up keys, but these keys cannot be backed up. Right? They only exist in a database. However, they can be recreated if I use the same parameters each time. So in that sense, they're deterministic, and I can recreate the key if I need in another database. So if I'm doing something like replication and I've got data encrypted, I can create this key on both databases, the publisher and the subscriber, and I would be able to do the encryption or decryption. Right? These require more resources than hashing. It's definitely a lot more resources than hashing, but it's orders of magnitude less than asymmetric keys, which we'll look at next. Okay? Typically, we protect data with symmetric keys, and then we use additional protection on the key itself. There's these parameters. These are the parameters that actually have to be the same, so we'll show you those. So let's look at how those work. So let me use my database. I'm going to create a little table here, put some data in. For those of you who don't know, I live on a ranch in Colorado. It's a working horse ranch. I have kids. My kids have jobs. They get paid less than me because I'm king of the ranch, and it's just the way life goes. So let's encrypt salary. So I'm going to add a column, a binary column, because encrypted data is binary data. Okay? And then I'm going to create a key here. This is similar to what we did with the TDE. I pick an algorithm, I add in parameters. These become important to my key. Okay? These start to become items that I need to protect in order to ensure that I can keep this data safe. So the values that I would use here in testing and development, I would stick in source control. I would not necessarily use those same values in production. Okay? Just so you know, because this could, otherwise your data is not necessarily protected. To use the key, I have to open it. In this case, I have to supply the password. If I had done encrypted in some other way, I could, potentially just get by here, decrypt it a different way. But in this case, I supply the password. I'm going to encrypt the data here, and then set the old value to 0. I just pass in the value here into this encrypt by key function. This asks me for the GUID of the key, so I use the key GUID function. I don't know where else we use this or why. I don't know why I can't just pass in the name of the key, but such is the way Microsoft wrote it. So if I look at my data, I set these to 0. Here are my encrypted values. Typically in a real application, we would remove this column. We would just have the encrypted data there. Now, if I want to decrypt the data, I use decrypt by key, and it doesn't work. And the reason it doesn't work is because I actually have to cast these values back to the original values. This isn't well documented. This is one of those things that drove me crazy when I started working with encryption. But you just have to remember to cast it back the way that you had stored it to get the real values back.
This casting or this thing you can do in the front end in the programming, not necessary to do in the back end? Could I do this in the front end or instead of the back end? The casting I need to do when I do the decryption in order to get this value back. But I could do encryption in the front end as well. All of the way this encryption works, there are .NET classes for almost all of this. As a matter of fact, it's probably the same classes that are implemented in SQL Server.exe. But you could do any of this encryption in the front end. The way that it works in .NET is really similar to this. You pass in, you have a key, you have to unlock that key essentially with your password or however you have it protected. You pass in a string of data, and you get out an encrypted value, or you pass in an encrypted string and you get out a plain text value. Hey, it's all very mechanical. Yes?
So if you could slide over, go back to that last result, query result, and scroll over, because the beginning of the encryption is the same. Must be using like a block level encryption.
So he's noticing that the beginning of encryption is the same. If you look up into about this point in here, everything is the same on all sides. So if you notice anything interesting about the decrypt by key function, I don't pass in the key. So there's a header on all of this data that actually tells it which key was used. So that's essentially what you're seeing there. It's not really a block level thing like hashing.
So where is your, when you create symmetric, where it is stored?
Where is the key stored?
Yes, it's stored in the master or it's stored?
No, my key is stored here. So all my keys are stored in the security, users and roles. Asymmetric keys, certificates, symmetric keys are all stored here. Okay.
And any alteration is possible from here, this place, by looking this one? No.
Any what?
Alteration or changes?
So I don't really have anything I can do here.
I see. Okay. So this is just to view, you have an encryption key implemented.
This is just to let you know encryption keys. The way that these encryption keys work is that they have to be opened in the session. I can close them in the session as well, but I have to open them. You'll notice I did that right here. I have to open this. There is no grant, revoke, deny on these keys. So I can't have permissions flowing through here. I have to have this password. This is the second place where you can protect your data from the DBA. If they don't have the password or the ability to open up a key, they cannot read this data. Okay? So this password now becomes a key. This is what becomes what I have to protect. Now you made me lose my place. All right, so my son is very smart, he's creative. He decides that he wants a raise. He decides to hack the table. All right, he doesn't have to break the encryption. All he did was do an update, right? And he's giving himself a raise, and his mom cuts the checks. You know, he's having a good week, right? New Xbox One. This is, again, why SQL injection is a big problem. It is a huge problem. Please, do not write dynamic SQL or use queries that access your database without parameterizing everything. Because this kind of thing can happen through SQL injection. This is how you lose data. Even when you've got strong encryption. Right? Don't have to know the encryption password, don't have to know how to decrypt things, anything. I can just hack data and get past the encryption this way.
So you basically did the encryption salary from that column and just copied it over?
All I did was an update statement.
Yeah, okay. So
This is a simple thing that will fly through SQL injection easily and cause you problems. Imagine if somebody decides, the secretary decides to send this in your HR application, everybody gets paid what the CEO gets paid. That's a bad day. That's an RGE. Maybe not for the DBA, it might be for the developers. But this is why SQL injection is a huge problem, because encryption doesn't protect against it. All right? What can we do? Let me fix my table real quick and go back to this. I'm going to add a new column here. I'm going to add a row GUID column, which is just a GUID. And I'm going to populate it. And then you can see that they're different for every row here. And I fixed my salaries here again. So now let me re-encrypt the data. This time I'm going to do it with an authenticator. And I'll show you what that is right here. In the encrypt by key function, I pass in my key GUID and I pass in my text. I have this optional parameter that says add authenticator. This is essentially adding a salt to my encryption. Now this is a bit, I have to add this in order to provide the authenticator. You know, if I put a 0 here and I provide the authenticator, it doesn't do anything. It's two parameters that do the same thing, but you do need both in order to make this work. And in this case, whoops, what I've done is I passed in my row GUID here with that 1 in order to encrypt it. So if I perform the same attack again, it doesn't work. And the reason is because the authenticator that was used for the encryption won't allow the decryption to take place. So I've provided a salt here. Again, I don't know that I would use an authenticator in the same row as the data that I am encrypting, but perhaps I have a vertical partition or some other way of linking a GUID over to this row to provide authentication. All right? And let me clean up before I break something else.
So if your son, when he did the update, also included the row GUID, then it would work, any update?
Well, he doesn't get the chance to include the row GUID in decryption. It's
No,
only
in the update, if he updated both rows.
when he did the update? Yeah, so he could do that. If he did the,
If he knew.
he'd have to know that he couldn't just do the update. What he'd have to do is call the encryption again, right? Because that row GUID comes with the encrypt by key command. And then he would have to know which GUID to pass in as the authenticator to make it work. Okay? It still could work, and that's why you want to be careful. But he'd have to have access to that key for sure. Okay? We mentioned the algorithm stored in the header, that's why you don't need it in there. You can generate temporary keys. Temporary keys is an amazing thing because I can, from my application, do a create key, pound, whatever, encrypt data, drop the key or close my session, the key is gone. The key to decrypt the data never exists in the database outside of a session. That could be another way that I protect data from the DBA because the key never exists in the database at all. It's a very powerful feature. I can also do encryption with passphrases instead of using symmetric keys. It's triple desk encryption, which It's what your banks use, but it's not really great encryption. Not these days. All right. Any other questions about symmetric keys before we go on? I'm running low on time. Ike's going to kick me out in a minute. How much time, man?
You're fine. We've got like maybe 10 minutes.
Okay. All right, so asymmetric keys. There's nothing in the real world that's like an asymmetric key, because the key that I use to do the encryption is not the key that I use to do the decryption. They're completely separate. This is based on some complex math and factoring prime numbers. Essentially, when you generate these keys, you generate a pair of keys, and they are linked together. And so one of the keys does the encryption, and the other key does the decryption. So the way this works is, if I take text and I run it through my first key, my red key, I get a result. Now this result is this result. Just trust me because I did it. I cut and pasted it. If I take this result and I run it through key 1, I get a mess. I do not have the ability to decrypt it. Instead, what I need to do is I have a separate key. And these two are paired. When I first generate these keys, I get a pair of keys. And when I run text through one key, I run it through the other key to decrypt it. I could reverse these keys. I would get different results here, but this process is the same. One does encryption, the other does a decryption. If the other does the encryption, then the first does the decryption. All right? We typically call these public and private keys. You may have heard that term. Public key encryption or public-private encryption, or if you see PKI, the public key infrastructure, that has to do with managing these keys. What we have typically is the private key is private. It's to the individual, the organization. It's kept secure and you don't disclose it to anybody. The public key, you publish to the world and everybody in the world can see it. Everybody in the world can use it. The reason we do this, anybody can encrypt data with my public key. Because I publish it on my website, it's on my business card, everywhere else. But only I can decrypt it. That provides a secure channel, provides guarantee that you can send a message to me and only me. Right? Same thing for it's an organization. Right? Guarantee that only that person can read the message. I can encrypt data with my private key. Anybody, I just realized I had a colored one. Oh. Anybody can decrypt it with my public key. Anybody in the world. What's the value of that?
Proves their identity.
It's a digital signature. It provides authentication so that only I could have sent that message, or only my organization could have sent that message. How do we use these? I encrypt data with the private key. Then I take that result and I encrypt it again with my partner Andy's public key. 2 encryptions. Andy decrypts the outer message with his private key. Right? Only he can do that. He then takes that result and he decrypts it with my public. Guaranteed the message came from me. This provides me a secure channel to communicate with Andy without having to exchange keys. Every other cryptography system in the world, the main weakness, the problem we have had is when you have to exchange keys. We have to physically get together to exchange keys somehow. In this case, we never have to exchange keys. The public keys are out there, but we never have to exchange anything else. So this is how SSL works on your websites. This is how you can guarantee, without ever having gone to ohgolly.com or amazon.com or anywhere else and exchange keys, that you can be sure you communicate with them. Because you're using their public key to do work. And they're using, it's a certificate, but essentially it's the same thing. All right? So, how do we do this stuff? There's standard DDL in SQL Server. There's also 2 utilities that you can use, one from Visual Studio SDK, one from the Windows SDK. SN is strong name. This is how you create asymmetric keys for signing of your code. Certificates, create your own certificates if you so choose. And we saw how to create certificates earlier in TDE. You can encrypt with password these just like I did for the symmetric key. And then typically the way that we do this is that we use asymmetric keys to encrypt symmetric keys and symmetric keys to encrypt data. The reason is these require a tremendous amount of resources to work with. This is orders of magnitude worse than symmetric keys. So we don't want to use these to directly encrypt data. We can, but it's a huge resource drain on your server. So typically we just protect the symmetric key with an asymmetric key. and then the symmetric key does the encryption and decryption of your data. All right? Certificates are asymmetric keys. They're public-private pairs. Matter of fact, if you remember when I copied over the certificate from one instance to the other instance, I had to copy two files. One was the certificate public key, one was the certificate private key. Copied those over. The expiration dates are not enforced by SQL Server, which is good. All of us, I know I would at least, forget to renew a certificate or forget to check the date and it would expire and I would have data encrypted with it. And if I couldn't decrypt the data, that would be a really bad day. So the expiration date on certificate used for encryption here is for your edification only. It is not in any way used to protect your data. It's only there so you can query it, and then you have to be responsible for decrypting and re-encrypting the data with a new certificate. Okay. SQL Server increases the longest length. Please use long lengths. I'm just going to do a quick demo of this. I'm not going to go through the whole thing, but you can have the code. It works the same way. I can create an asymmetric key, just like create a symmetric key with an algorithm. I can encrypt data here, and I get an encrypted result. If I take this result here and I stick it into my decryption routine, it decrypts. So that's not really my salary, it's just wishful thinking on my part. I have a make cert command I could run. This would be run from a command prompt, assuming I had make cert.exe available. It would create a certificate. I would load the certificate the same way I did earlier. The way that, here's certificates, I'm not going to do this because I'm running out of time. Here is where we would typically do this. I would create a symmetric key encrypted by my certificate or by my asymmetric key. This is how I do the protection. And then what I would have to do is I would open up, once I'd opened up the certificate or the asymmetric key, then I could easily use the symmetric key because it would decrypt the next one in that hierarchy. And then I would do the same thing I did before, essentially, where I'm encrypting data. All this encryption is essentially call a function, pass in the key and the data I want to encrypt, or call a function where I have the encrypted data and it will decrypt it. That's essentially how all this stuff works. Okay? Once you get past that, it's not that hard to work with. The hard part becomes making sure that you have backups of all your keys and managing your keys. All right? The last thing I want to talk about here is key length. Please use long lengths. Right? The reasons are that there are ways to attack various algorithms. In hashing, MD5 and SHA-1 have essentially been deprecated because they have been successfully attacked. So you don't want to use those. Please use SHA-2 or 3 if you have the chance. A few years ago, the DKIM certificate protects mail systems, email systems around the world. A gentleman figured out that he could crack Google's 512-bit key certificate, and he did so, and he sent email from Sergey Brin to Sergey Brin, or Larry Page to Larry Page, some of them, and they were understandably upset, and pretty soon they hired the guy and changed their certificate as well. As of last fall, a 384-bit key could easily be cracked on most laptops that we use today, at least most new laptops. 512-bit key could be cracked about $75 on AWS last fall. $75 is within the realm of a joke to bother a friend of yours. It's certainly within the realm of any criminal that would so choose to do so. Okay, 768-bit keys can be cracked by large companies, small countries, that kind of thing. You should really be using keys that are as long as possible. And in certificate and asymmetric key levels, I would say 2048 or better at this point in time. And this changes all the time because computers get faster and people figure out how to do this stuff. All right, we're about out of time. If you got questions, I'll take questions real quick. I have to run over to the other room, so come up front, otherwise I'm going to start packing up. Please fill out your feedback forms. There's cards with the URL, and if you don't know where they are, they're somewhere over by those tables and desks over there. And then you can download this stuff from either SQL in the City site, or from my blog. I've got this code and demo, and you can run it yourself. Thanks for coming. I hope you enjoy it, and I apologize for joining. If you have questions,